resonance or an inductive effect?
I think inductive.
Exactly, it's an inductive, right? Because for a resonance effect, you need to be in conjugation with this. And for most electron withdrawing groups on the carbon adjacent, since this carbon's an sp3 carbon, you don't get, it's not in resonance, not in conjugation. So it's almost entirely through an inductive effect. And let me show you a classic example in orange. Trifluoromethyl acetic acid. So acetic acid is at pKa of 4.5. This is a carbon with 3 fluorines off of it. Does anyone want to guess what the pKa of trifluoroacetic acid? Sub-zero. One's a good guess, but it's like 0 to -1. This is so acidic, it fumes. So this is trifluoroacetic acid, and has a pKa that is less than 0. In general, the more electron withdrawing groups you have adjacent, the stronger the effect. So I should probably check my notes to have the right number. But if you have 1 chlorine adjacent to your carboxylic acid, so you have monochloroacetic acid, I believe that's a pKa of about 2.85. Whereas if you have trifluoroacetic acid, trichloroacetic acid, it now has a pKa of, I believe, a little less than 1. I believe it's 0.85. And of course, chlorine is not as good of an electron withdrawing group as fluorine. So that's why TFA is more acidic, because fluorine is a better electron withdrawing group. And so the way this works with the inductive effect is, we'll do it for CF3. We have these fluorines, which are very electronegative, and so they like to take in the partial minus charge from the system. So they're withdrawing electrons through this bond from this carbon. So what that is doing is giving this carbon a very good partial positive charge. All right? And then this partial positive charge is going to be relayed to this carbon, which already has a partial positive charge, and belong, and so on and so forth. And so what that means is, I'm doing some magic Bohr chemistry and giving us the anion. So why is a typical carboxylic acid acidic? Resonance, right? Because you can resonate this minus charge into this carbonyl to have a resonance structure that looks exactly like this, just flipped. And so resonance is enough to give it a pKa of about 4. Resonance is enough to give sulfuric acid a pKa sub-0 because sulfuric acid has more resonance structures. So the reason why TFA is so acidic is not only does it have the resonance, it's got this partial positive charge being relayed from the fluorines to this carbon, and from this carbon to this carbon. And so because there's a greater partial positive charge at this carbon, that partial positive charge helps stabilize this partial minus charge. And so the inductive effect is spreading out the minus charge. So let's draw the resonance hybrid. So the inductive effect is taking this minus charge that's spread out among these 3 atoms in the carboxylate and now withdrawing it into the carbon in the 3 fluorine groups. So that's giving more electron delocalization and more stabilization. So it's stabilizing the carboxylic acid through the inductive effect. So something I've said time and again in my lecture is the inductive effect is heavily dependent on space. And so just let me give you an example. So here's monochloroacetic acid again, has a pKa of 2.85. If we remove the chlorine one atom further away, so instead of being a carbon adjacent to the carboxylic acid, it's now 2 carbons away from the carboxylic acid. It now has a pKa of roughly 4. So by moving the chlorine one atom away, it still has a tiny effect, but it's not nearly as marked as when it's closer. So once again, the inductive effect roughly falls off with R3, where R equals the radius from the inductive group. So it doesn't fall off linearly, it falls off to the third. So very, very, very quickly it falls off. And so this shows nicely, just removing the electron withdrawn group one more atom pretty much completely attenuates the effect of the electron withdrawn group. So, and the similar inductive effect you will see basically with every single carboxylic acid group. And remember what I said here, what we're pretty much doing is by inducing a partial positive charge here, we're increasing the partial positive charge here as well. So the partial positive charge induced at the carbon with the 3 electronegative atoms, it's going to want to spread out because charges like to spread out, and so it's going to try to take whatever electron density the carbonyl carbon has, but the carbonyl carbon is pretty electron poor as it is, so it doesn't have much. So it's like taking from the poor to give to the rich kind of deal, and so this becomes even more electron poor. So pretty much what the inductive effect does is it makes our partial positive charge on the carbonyl carbon greater. And of course, that will stabilize this because now there's a positive charge closer to the atom. So we're going to be talking in this chapter a lot about nucleophiles adding into various of these carbonyls. And the general thing to realize is if you have an electron withdrawn group close to your carbonyl carbon, it's going to be more reactive because that electron withdrawn group is removing electron density from the carbonyl carbon, making it an even more partial positive charge than it did before, and hence more reactive. So electron withdrawn groups makes electrophiles, at least carbonyl-based electrophiles, more reactive. And so the chemistry we're talking about in this class, and this is pretty much going to sum up every mechanism in chapter 17. And I've said this at least once in this class, and I'll say it again because I like it. Chemistry, specifically organic chemistry, is a variation of itself. Especially this class. Every mechanism in this class, you can argue, is a variation of something you've seen previously. And that is the very, 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 very important truth for this class, particularly chapter 17. I'm probably going to show you 20 different reactions in this chapter. And in my opinion, mechanistically, they're all really, 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 really similar. And they're all going to be of this vein. We're going to take a carbonyl with a leaving group. We're going to take a nucleophile. The nucleophile is going to add into the carbonyl to give us a tetrahedral intermediate. Okay, and then in the tetrahedral intermediate with the O minus, these electrons are going to kick back down, kicking off either the nucleophile or the leaving group. if it kicks out the nucleophile, which I'll do in red, it will just give us the starting material back. If it kicks out the leaving group that was originally in the carbonyl, which I'll again complete in blue, it will give us an acyl group where we swapped out the leaving group for the nucleophile. And the equilibrium of this reaction, going from the carbonyl of the leaving group to the carbonyl of the nucleophile, is going to be decided by the difference in pKa's between the nucleophile and the leaving group. So reaction starts, we have nucleophile swimming around with the carbonyl of the leaving group attached to it. Nucleophile attacks, kicks off the leaving group, giving us the acyl group with the nucleophile attached, plus the leaving group swimming along. But of course the leaving group can add in, give us this, and eventually go back to this. So this is a completely equilibrium situation. And the thing that's going to determine it is the stability of the nucleophile versus stability of the leaving group, which can be nicely annotated by pKa's. So the more stable species, nucleophile leaving group, that's going to be where the equilibrium lies. The equilibrium is going to lie with the more stable species. So if the leaving group has a lower pKa, meaning its conjugate base is more stable than the nucleophile, then the equilibrium is going to side towards this product because the leaving group is more stable than the nucleophile, so we're favoring that. However, if the nucleophile is more stable than the leaving group, then it will favor the starting material. Because why would the nucleophile do something to give a less stable product? And the way we annotate this is going to be with pKa's. Now, you'll see a million examples of this. But the key thing is you draw your reaction and you ask, what's the more stable species, the nucleophile or leaving group? And you annotate stability by what's the pKa of the conjugate acid. And the lower conjugate acid wins. So whichever side of the equilibrium has the lower conjugate acid is going to be the side that the equilibrium favors. Let me show you an example. What's that? Yeah. What's that?
Oh, you already erased it.
I didn't erase anything. I just put something behind it. This?
No, I was wondering because I want to go back to
This.
No, I didn't.
It was just this behind it.
Oh, yeah, I was just, could you read that first?
Yeah, I want to erase it. I want to erase, okay. I just need more space to write, so I want to erase it and you can take a picture of it or draw it after lecture. And I want to erase it so after lecture you can draw it down. So, so a classic example of this is the reaction of an acid chloride. And an amine. So, an amine plus an acid chloride, the amine will add in theoretically to the acid chloride. Give us our tetrahedral intermediate, which is given by this arrow. But chemists don't draw the tetrahedral intermediate all the time. What they do is they draw the first arrow designating the tetrahedral intermediate, and then they draw the second arrow, and then they kick out the leaving group. That's how chemists draw, because it's a lot quicker than drawing the tetrahedral intermediate. And you can draw this too. But just because I'm going to be nice, I will draw the tetrahedral intermediate this time. But realize in general, we do this because it's much quicker. So brackets mean intermediate. So it gives us this. And now it can kick up two things. It can kick up this as the ammonium, or it can kick up the chlorine. What's the pKa of a Cl minus? Well, what's the pKa of the conjugate acid of Cl minus, which is HCl? 0. What's the pKa of the conjugate acid of this leaving, which is an ammonium? About 10. An ammonium pKa is 10. So by 10 orders of magnitude, it's going to prefer